start that. For all x unequal to c in some interval about c, then the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x equals L. Then the limit as x approaches c of f of x equals L, which I think makes perfect sense, totally, without further explanation. So moving on to example, no, I'm just kidding. That was a joke again. So it's a weird one, but I think if you really kind of dissect it, it should actually make perfect sense. Okay, it's just, this is another case of a mathematician or a textbook author attempting to impress their peers, which is generally the case whenever you see anything online in textbooks. If you're looking for an explanation other than, you know, like Khan Academy and stuff like that, if you're looking for an explanation of how things typically work, and you find a nice video or something, or you find the title of a video that seems to make perfect sense as to what it is you're looking for, and then you start listening to it, and it's just making the situation worse, that's because the person there doing the video is just trying to impress people, right? And so the idea here is to not do that, is to try to actually explain it. So I sent out 2 videos. It'll come at like 9:30, I think, again. They're actually Khan Academy videos, but they're related to epsilon delta. They rehash a lot of the same stuff that I said, but they extend on it in a numerical sense. So if you had a little trouble with that separate problem I sent out yesterday, the videos might actually help with that. So it's a recommended listen. All right. So anyway, what this is telling us is that if you have a function that's in between 2 other functions, then if you were to take the limit of those 2 outer functions at a particular c value and get the same result, because this function is squeezed in between those other 2 functions, they would necessarily have the same limit, or it would have the same limit as the 2 outer limits. It's when the 2 outer limits are different, that's when you have a problem. All right. So and that's why I prefer the squeeze theorem, because you have one function being squeezed in between 2 others. All right. So if you have a limit here that's the same as the limit there, and you know this is in the middle of these 2, then they would necessarily have to be the same. All right. So that's all well and good in theory. This is another case of, I show you a nasty formula that doesn't necessarily equate to a process. All right, so that's what we were talking about yesterday. All wise-assery aside, you have theorem and then some practical approach. The practical approach doesn't always emerge obviously from the theory. So let's see if we can kind of figure this out. I don't know if I want to start with this example though. Let me actually start with example 2. So I'll take that as a typo, because example 2, if memory serves, is the one that was from the continuity lesson. And that would be a good place to start. So if somebody wants to submit as a typo, swap examples 1 and 2, that I would take that. All right. So let's go with number 2. All right, so as promised, here's the payoff. It's the analytic approach for figuring out this limit. The one that does not, you got it, boom. And there it is, yeah. Yeah, the key to that is getting a sense of when I'm going in that direction. So, don't wait for me to complete the thought. Yeah. You got to start taking action the minute. So, typo on page, you have that ready to rock and roll. And then the minute I complete the thought, you're ready to go. Okay. So, anyway, what we're looking for is 2 functions that this guy might be sandwiched in between. or squeezed by. All right, so that's the challenge. If you know that, the job's pretty much done. All right, but let's focus on something that we would consider to be a known quantity. Like, for example, a sine function. Whether it's sine of 1 over x, sine of 10x, sine of pi x, whatever, the result of that function is always going to be between what and what? Negative 1 and 1, right? All right, so what we're going to do is we're going to start with a known inequality and build our way to the expression that was given to us. All right. Fortunately, in this case, there's not much building to do. All right, so if I want the middle expression to be the given, so I want this to become this whole shebang, I want to multiply, oh, that's just poor quality. I want to multiply the whole thing by x squared. So we'd be looking at negative x squared less than or equal to, I'm going to leave a little room here for no apparent reason. And then leave a little room here for no apparent reason. That's not true, obviously. There's a good reason why. All right, because what I want to do, and this is where the rule comes in, is I want to find the limit of all three parts as x approaches 0. Let's see. So, limit as x approaches meh, an additional meh, and one more meh. 3 mehs. All right, the two outers we should be able to get just by using analytic approaches, aka substitution. So plug in a 0 for x and you get a 0. Plug in a 0 for x and you get a 0. All right. Prior to applying the limit, we were justifying the, I forget what the order was, and I don't want to scroll back, but the f of x, g of x, h of x relationship, where one function was in between the other two. So we developed an inequality that was true based on appropriate mathematics. So what we're getting at is the idea that this, whatever it is, has to be in between these two functions. Y equals negative x squared, y equals positive x squared. So if we apply the limit to this, limit as x approaches 0, and the limit as x approaches 0 to this one, if we get the same number, then the limit of the original function would have to take on whatever that value, because basically it's saying, all right, I don't know what the limit of this expression is, but I know it's between 0 and 0. And you're like, okay, well, duh, it's 0, all right? So we now know what the answer is. Something we got visually last week, maybe Monday, I don't know, one of those days. But we now know that the limit is equal to 0. We got it graphically, now we got it analytically. Question?
Where did negative 1 and 1 come from?
Oh, a sine function has a range if you actually draw a sine wave, yeah. So sine of x over x as x approaches infinity. All right, so let's take a look at the graph real quick. do a zoom trig. All right, so if you remember your limit rules for, special limit rules for trig, you might remember that the limit as x approaches 0 of sine x over x is equal to 1, and that's illustrated here. But as x approaches infinity, definitely not 1, we're going out in the positive direction. It's just a question of, is this leveling off, or is it going to oscillate back and forth? What's the story? So what you could do graphically is extend your window, get a visual sense, go to the table set, make it 0, something big, and then scroll. It does appear that it's going to 0. Right? It's oscillating back and forth between positives and negatives, but in doing so, it's actually getting closer and closer to 0. But if we need to show analytically that this is a limit that actually is equal to 0, then we have to do something else. All right, so we can try a couple of things. We could start with what we started with over here, and that is the sine of x is between -1 and 1. Reasonable piece of information. All right, so some known fact. Now we just want to manipulate this expression in order to get, and by the way, I said there's a couple things that we can do. There's a way to do it that doesn't involve starting with the sine function, but we'll cross that bridge when we get to some of the practice examples. I want to make the sine of x into a sine of x over x. I think that's easy enough. You just divide everything by x. So then we would apply the limit. As a shortcut, I'll accept this. After you've done your algebraic manipulation, if you want to apply a limit the way I'm writing it here, it's implied that you're applying a limit to each part of the inequality. Right? The one thing is when you're actually applying it, you can numerically apply it to the outer bounds, but you actually have to write it for the inner one. Right? So it's like saving you half a step. So the limit as x approaches infinity of -1 over x would be what? 0, less than or equal to the limit as x approaches infinity of sine x over x is less than or equal to upper bound? 0. Upper and lower bounds are the same, so we can conclude that the limit as x approaches infinity of sine of x over x is in fact equal to 0. All right, so you might be wondering, okay, we're focusing on sine here a little bit. What about cosine? So play out in your mind this exact same process for cosine. So just step by step. Would you get a different answer? No, right? Because this would become, cosine also exists between -1 and 1. So the first step would be the same, except it would say cosine. Then you would divide by x, or you would divide by x here. Apply the limits and the outer bounds, you still get 0. So what we would determine using the same exact approach, except replacing sines with cosines, is that you're also going out to 0. And you can verify it graphically. And it should make sense visually, because a cosine wave is just a translated version of a sine wave in general. It's a translated version of a sine wave in general. So a lot of the properties are going to be similar. right? The only difference, obviously, would be how the denominator of x interacts with the cosine as opposed to the sine, right? There are other instances, different instances in which the cosine function would be undefined or indeterminate, whereas with the sine function it plays out a little differently. But for extreme values, as they get larger and larger, you start moving away from any possibility of having something that would be indeterminate or undefined. It becomes more and more consistent with the sine function, right? Okay, so let's take a look at number 1 below. There's 2 minus cosine x, and then we're dividing by x plus 3. Although, I guess it's fine. Yeah, I'll do this one. All right, because numbers 2, 3, and 4 are just jazzier versions of what we're going to do in number 1. So if you're with me on this process, we should be all right. So we have a 2 minus cosine of x is part of our numerator. We could try to come up with an inequality that plays to that and then go from there. We could also break up our limit into 2 separate limits because we have a subtraction in our numerator. That's actually the approach I want to take, because even though you can get it the other way, I want to show you how you would do it if you had something that's completely variable based, so without the trig in it. So let's rewrite this as the limit as x approaches infinity of 2 over x plus 3 minus the limit as x approaches infinity of cosine x over x plus 3. All right, so one thing to keep in mind is that these are proofs. So you might look at this and say, okay, this is 0 just because. All right, but that's not a proof. Right? If we're using the squeeze theorem, we want to take a particular approach. This one, very similar to what we were just talking about. Slight adjustment. This one, a lot different. All right, but hopefully not confusingly so. So we'll see. I'll try my best. But we'll focus on this one for a second. We know cosine is between -1 and 1. And we know we could divide each part by x plus 3. All right, so and then once we do that, we could apply our limit. All right, so outer bounds in both cases. Again, it's kind of fishy because I'm telling you that in a second that we're going to have to prove this using a different technique, whereas here we're going to use an intuitive approach. The instructions on a quiz or a test will be very clear as to what you need to do and what you can kind of skip steps on. But anyway, you gotta do it. All right, so lower bound we're going 0, upper bound we're going 0. So we're saying by the squeeze theorem, that the cosine part of this expression is equal to 0. All right, so again, this component here we're doing intuitively, but now I'm going to show you how you would do it explicitly, right, using the squeeze theorem. Hmm.
Why did you change to x versus 0?
Oh, because I was not thoroughly paying attention to what I was doing. But I appreciate the benefit of the doubt. So, this guy, let's learn how to do it analytically using the squeeze theorem. It'll be pretty interesting. Just like in the case of, I'll just do it like this. Just like in the case of the trig stuff, we're looking for some definite relationship that exists, right? So the issue is we don't have something nice like with a cosine or a sine function between -1 and 1. But then you think about it, if you had something like, I don't know, a secant function or a tangent function, you'd have to make some kind of adjustment there too. You know, because like a secant function is not bound between -1 and 1, but the reciprocal of it is, so maybe you could do something with that, right? Here, you don't have any of that to rely on, but we have some rational function relationships that we can rely on, right? So what I'm going to do is I'm going to look at the parent function that would exist here, all right? Just a simple parent function, 1 over x. All right, the parent function of any rational function is just 1 over x. It's how you manipulate that makes it into the other rational functions. Do you then incorporate a numerator factor? Do you translate it horizontally? Right? Any number of possibilities. Do you raise the variable to a power? Right? All sorts of different things going on there. Right? So, but what I do have here is an x plus 3. So let me make a note of that. So which one of these ratios is bigger? 1 over x or 1 over x plus 3? The 1 over x, right? Because in the 1 over x plus 3, you're dividing by something larger. So I have some finite relationship there. I can go the other way around if I want to make my life a little easier. All right, so we have some relationship that we could rely on. Now we just have to do something with this. The issue here is that we could be looking at a size relationship that is either positive or negative. And so what we're gaining from this is the idea, kind of like the epsilon delta stuff, is that the 1 over x plus 3 could be between the -1 over x and the positive 1 over x. All right, and we could flesh that out visually. We'll talk more about absolute value stuff tomorrow because there's a visual way of representing it that kind of clarifies any misconceptions. And what I've noticed over the years is that there's a lot of them. I'm going to type this in as. So, -1 over x, positive 1 over x should surround the 1 over x plus 3. So let's take a look at it. I can give you the short version of it today, but there's more to it than that. All right, now we're focused on, well, infinity. So it's kind of, I mean, it's kind of a mess, but if I just focus on the extreme values, so if I start at 0, for example, and get it close to the x-axis, so like relatively close anyway, -2 to 2. You have 3 curves and one of them sandwiched in between the other. This approach really allows us to capture the function because by negating it, by attaching the absolute value, you're taking a reflection over the y-axis, the x-axis, right? So if you know that this relationship is going to bound, so this one is below this. So if this is going to bound this function on the high side, by throwing an absolute value on it, we allow a new function to bound it on the low side, just simply by reflecting over the x-axis, all right? And that's something that's kind of been missing, maybe from your instruction. The whole idea of an absolute value.
Yeah.
Because, and it's very kind of disheartening, but let me just give you the quick version here. Very, very quick. Zoom 6, the line y equals x, standard function, right? So an absolute value takes any function and makes it non-negative, right? So it takes a number, makes it non-negative, so why wouldn't it do the same thing for a graph? So I have a line here. Here's my negative part of the line. Absolute value will make that non-negative. All right, but when you apply an absolute value for something, what it's telling us is that you're allowing for positive or negative results to exist. So that's really saying that if you're just looking at 1 over x plus 3, it could be positive or negative, but I'm guaranteeing that the result would be positive, so the size relationship will be maintained. All right, so I have an activity tomorrow that's going to really help flesh this out. So I think hopefully it'll make a lot more sense then. Because in Calc 2, I was going over the concept of areas, and well, I'll just give you that real quick. There's like some crazy functions, you know, something like this, maybe it's piecewise, and you have to find the area contained between the function and the x-axis, but only positive areas. And so since the calculator would just report negative areas if it's below the axis, by taking the absolute value of just this component, can I draw a reflection? I don't think I can. Oh, that hurts so much. All right, so this goes to there and reports a positive area. All right, so it would give you the equivalent area, but positive. And so there is a benefit to really having a good understanding of absolute values. And also in the epsilon delta stuff, absolute values were coming up, so definitely worth our time. All right, so outer bound, 0. Inner bound, well, inner function. Oh, I put a equal sign. All right, so here's a little weirdness for you. So we say 0, and then we have 0 plus 0 equals 0, so the final answer is 0. So the two parts. But a good question that I've gotten over the years, and it seems like this would be some kind of contradiction, but it's really not. How could you be greater than 0 and less than 0 at the same time? Wouldn't there have to be some kind of equality? The idea is that a limit is never actual, well, it's not always attaining a particular value, it's going to a particular value. So this relationship is true, certainly. For small values of x, 1 over x plus 3 is definitely, without a doubt, less than 1 over x. But for very, very large values of x, 1 over x plus 3 gets closer and closer to being the same as 1 over x. So that if you could ever get to infinity, then it would actually be the same thing, right? Because they have the same end behavior. So this relationship is true for small values of x, but once you get out to infinity, now you can actually assume the equality, right? Very weird to think about. It's kind of like you're finding the limit of a limit function. You're saying, what would be the limit of this limit problem for very large values of x?
Why does the right side have equals to inequalities and the left doesn't? Like in the other part of the
Oh, the other part.
work,
Let me
the
zoom.
One has greater than or equal to, and one the left side doesn't.
Because a cosine function can actually be equal to negative 1 and 1.
Okay.
Here, for small values of x, not necessarily. All right, so basically, long story short on this one is that we allow for this slight contradiction to exist, because even though it's not necessarily true for small values of x, for large values of x, we can think of it as meh, meh, for large x. All right. But you don't actually have to write that, because you're, in all likelihood, I don't want to insult, but it's happened. It will happen again. In all likelihood, you're going to forget. And I don't want to take off the half point. And also, I'm probably going to forget to take off the half point anyway, so why even bother, right? Because I have digital versions I can give out. All right, so same idea for number 2, at least initially, as it was for number 1, where we could break it up by the minus sign and then go from there. The other possibility is to kind of build it from scratch and just look at the denominator. The whole idea behind the squeeze theorem is to kind of pretend you don't know things like end behavior model, just like intuitive ways of finding limits. You're looking for a purely analytic approach. So you want to justify all of your steps in some way that does not involve looking at a graph, right? So end behavior models are wonderful because you could actually make a calculation, something like 1 over infinity, we know that goes to 0. That's more than an assumption, that's just, number sense, all right? But if you were to say 1 over x plus 3 goes to infinity because there's a horizontal asymptote for that function, that's more of a graphical way of explaining it. It's not analytic, all right? So you would not get full credit for that, and it would not be fun. All right, so we have a relationship between the parent function 1 over x and 1 over x plus 3. All right, what was that relationship again? 1 over x is greater. All right, and that's because the 1 over x plus 3, the x plus 3 is a larger denominator. You're dividing 1 by more on the right than you are on the left. All right, so if you want to skip this step and go right to the next one, that's fine, because what we want is a less than symbol, because we generally want to make a compound inequality. All right. We throw absolute values around this. For now, we're just kind of taking it for granted. We haven't done the absolute value activity yet. But really, the justification was that we want to be able to surround this expression, which is the heart of this guy. We want to surround it with 2 other functions that we can find the limit of in some way, all right? And then eventually build towards the one that was given to us, all right? So we know that if we slap absolute values on the 1 over x plus 3, it's going to give us a new compound inequality of negative 1 over x less than 1 over x plus 3 less than 1 over x. All right, so we could take this approach and see where it goes, and that's with the squeeze theorem often how it's going to play out. You want to see how the situation is going to work. you can, like I said, you can also break this up by the minus sign and look at it as two separate things. Either way. So let's say you're going down this road, because we are. We would then multiply everything by the 2 minus cosine squared x. So we'd have, well, I'll distribute the negative on the fly here. Cosine squared x minus 2 over x less than 2 minus cosine squared x over x plus 3 less than 2 minus cosine squared x over x. All right, so we took this approach, we got to this step. Now we have a little bit of an issue because while we have simplified the outer functions a little bit, we haven't simplified them enough where we could just find the limit as x approaches infinity. So as a complete, and again, this is a complete and thorough analytic approach, so we're not making any assumptions here. If our job is just to find the limit, I would take a different approach, but I want to show you from top to bottom how a pure mathematician would go about doing something like this. Because AP graders think they're pure mathematicians. Reality is they're still high school mathematicians. Okay, so if you had a calculator available and you were actually to go into your calculator, figure out what these things are, that's again not an analytic approach, so we have to do something else. So let's take one of the extremes. Doesn't matter which one, because we're looking at this as kind of a multi-level problem. Let's take the limit as x approaches infinity, 2 minus cosine squared x over x. Bear in mind, identities are always a thing that you could rely on. So if you wanted to try something like, making this 2 minus cosine squared x, you could think of this as 1 plus 1 minus cosine squared x. You could then make this guy into what? Sine squared x. You could try to do something like that. The issue is it doesn't really get you anywhere for this problem, but that's why I'm not writing it on the big screen. But that is fair game. Identities are things that you should know, you should be able to apply. All right? They always come in the course in some fashion, not into every problem though. All right, so what we're going to do is kind of a multi-level thing here. Like I said, we're going to apply the squeeze theorem again. Okay, so we started off with the idea that a cosine squared, well actually we work with 2 minus cosine squared, but if you wanted to, you could just focus on the cosine squared. If you know what the range of a cosine squared function is, then you're done. I mean, that's the big challenge. But I guess the question would be, what if you did not know and, it was on your list of things to review before taking the non-calculator part of the AP exam, but it somehow just never got done. That, I suppose, could happen. Oh, wait, hold on. Thumb's not working right. So, cosine exists between -1 and 1. So the only thing I guess I could say would be to just take this and square it and see what you come up with. Obviously, it would be cosine squared. All right. If you square the upper bound, you'd still get a 1. The issue becomes the lower bound, right? So if you square the lower bound, you just get a positive 1 again. So then what are we saying? Cosine squared is between 1 and 1. That doesn't really make much sense because it's an oscillating curve, right? It's going to go up and it's going to go down. It's not constant, right? The other possibility would be that it's just this, simply less than or equal to 1. But that would allow for all sorts of negative values, so going down to negative infinity. So based on what we know about trig functions, that doesn't seem to make sense. All right, so you want to kind of analyze it off on the side or in your head and say you have a set of values between negative 1 and 1. All of these values, like a half, 7/8, 1/12, all of those values, if you square them, they're going to stay in that interval of 0 to 1. All right, so 0, then you'd be looking at 1 over 144, a quarter, 49 over 64, all between 0 and 1, right, and all the way up to a 1. All right, so what this is telling us is the set of values from 0 to 1 maps through the operation of a power of 2, so I'll just say square. Technically we write x squared above there, but you know, I don't want to get too fancy. It would map to the set from 0 to 1. All right, so that analyzes that part. So then the question would be, what's happening to all the guys on the other side? Negative 1 maps to a 1. Negative 1/12 maps to 1/144. 1/2, negative 1/2, maps to a quarter. So what we're getting from this is the set of values really from negative 1 to 1 will still map to the interval of 0 to 1. Right? That's a trial and error approach, but if you didn't understand what I was talking about graphically last time, then you got to fall back to something. So this would be it. And again, we're assuming that we're stuck in a position where we don't have a calculator available. What do? You know, if you have the calculator available, you just look at the graph. But this would be for those other times. So now we know where the cosine square function is going to exist between 0 and 1. So we could work off of that. So everything else that I did after that should have been fine. If you were confused about anything, it was probably this step. So I would negate the whole thing. Oh, sorry. Came up with an expression that logically wasn't true, so that was my indicator that I messed something up. All right, do a little switcherooski. Add a 2 to every part. So 1 less than or equal to 2 minus cosine squared. X less than or equal to 2. Then we're dividing everything by x. And then applying the limit. So the outer bounds would become 0, so that's where we would get the limit as x approaches infinity of 2 minus cosine squared x over x. And that's where the 0 comes from. And so that translates to what we did earlier as a final answer. Limit as x approaches infinity. 2 minus cosine squared x over x plus 3, because it's sandwiched in between those two, would also become 0. Yeah. A lot easier to do it this one. Slicing apples, by the way, is how I did this.
I'm a little bit confused. So you have the -1 is less than x or cosine of x is less than or equal to 1, and when you square it, I don't see where the 0 comes. Just, this is about what I missed. Okay.
Yeah. So if you square every entry in the -1 to 1 interval, they all will map into the 0 to 1 interval.
Oh, so you're not just squaring each piece.
Right.
You're thinking about what the square would look like. Okay.
Exactly. Very good. All right, and so number 4. Huh. Did I cover up number 3, or was there just no number 3?
There was. There is.
There's just no number 3.
No, there's no number 6. There is.
I'll see it.
Here, on your paper. It's right here.
So on your paper, there's a number 3.
Yes.
Yes.
Huh. Oh, okay. That's what happened. I was like, wait a minute. Like, what incarnation just happened? All right.
Mr. Camp, for the last one, why did you only do over x and not x plus 3 for the,
So
when you went from, yeah.
I was just looking at the outer limits, and so carrying that out, that's equivalent to that expression. And then once I have those, I knew that the inner one would have to take on the same value. Okay. Oh, I did it again. Number 3. So 3 and 4 are both equally disgusting looking.
Oh, yeah.
So the big challenge would be, like, where do I start? All right. So we could try working off the sine function instead of working it through it algebraically first. See where that goes. If you have a notable trig function, then it's usually a pretty nice place to start. Doesn't always play out. I'm actually going to take the negative along for the ride here too. Because positive or negative doesn't matter. The sine function is still going to be between -1 and 1. The negative coefficient just tells us which direction it's going initially. Instead of starting at the midline and going up, it's starting at the midline and going down. But it's still going down to a -1, and then when it swings around, it'll come back up to a +1. The 3 is the frequency. That just tells us how many times a sine wave happens in a 2 pi interval. So that's talking width, not height. So this is a perfectly reasonable assumption. And it also keeps us from having to do those extra steps, the annoying steps of negating, remembering to change the direction of the sine, and then moving things around. All right. So from here, I'll see where I go. I'll try adding a 5x squared to everything. If it looks like a multi-step problem in the setup, I mean, you look at that, you figure you got a lot of work to do. It's a pretty beefy expression. No matter what path you take, you're still going to have to do a representative amount of work. It's just a question of, you know, what type of work. All right, so we're looking at 5x squared minus 1 less than or equal to 5x squared minus sine 3x less than or equal to 5x squared plus 1. All right, and then divide out. And then we have to find the limit of this. All right. Now this is a good problem to go over in class because I can point out the mistake that you're likely to make if you were to make a mistake before you see a problem that's just like this on a unit test.
I would not have thought that maybe.
So here's the issue. Most folks, when they get to this step, they say the limit of this is 5 because I know the limit of this is 5. And that's really good. That's really great. It's a good observation. It's because you know your end behavior model, you know how to find horizontal asymptotes, all that stuff. The only problem with that is that's a graphical approach. No matter what you're writing down on paper, you don't actually have to produce a graph in order to use a graphical approach. You know, so I found the horizontal asymptote. All right, well, what's a horizontal asymptote? It's a line, it's a horizontal line. Graphically, it's telling us that you're approaching that mark as you go out to infinity or negative infinity. The issue is, since this is a proof, you need a completely thorough analytic approach. All right, so the algebra of calculus, which means anything that kind of pops into your mind without justification is not a sufficient answer. So, two possibilities. One would be to somehow try to simplify this and go from there. The other would be to actually just dive right in and see where it goes. All right? You'd probably just go after it, right?
Yeah.
You just dive right in? To do what? Yeah. Well, let's focus on this guy. Limit as x approaches negative infinity. Another level of the sandwich theorem.
Is that right?
Yep.
I don't know how to do it.
So I'm going to focus on the denominator. 1 over x squared plus 10 and its parent function. 1 over x squared. What's the relationship between these two?
1 over x squared plus 10
Is smaller, yep. All right. We want absolutes on this so that we can manufacture the squeezing. All right, so by taking the absolute, we're taking positive, negative, 1 over x squared. So 1 will be on the high side, 1 will be on the low side. In between those two would be this algebraic function. Well, if it were written as a function. Alright, then we'd multiply through with the 5x squared minus 1. And that would give us the middle expression. I'll just write it as negative parentheses. now the middle is what we were given originally, or what we had originally. Now we just have to find the limit as x approaches negative infinity, which doesn't seem like it would be too easy, but it actually is not bad now that we have the denominator down to a single monomial. Single monomial is redundant. All right. This is just a negative version of that. So whatever we get as a limit for one bound will be the same as the limit for the other bound if it's 0. If it's not 0, we know that we just have to take the opposite of it. All right, so what I'm going to do is just look at the limit as x approaches negative infinity. 5x squared minus 1 over x squared. Here's where you want to do a little simplifying. Little pretzel method. Basically just splitting the fraction, but I like drawing pretzels, so. Divide each part by x squared. Couldn't do that before because we had an x squared plus 10. If you wanted to actually carry out division, that was the simplifying step I was talking about earlier. If you wanted to do it, you have to do it with either long division or synthetic division. I didn't think you'd be overly interested in doing that, so figured you'd do it. All right. We have a difference in between the two terms of the expression. So limit as x approaches negative infinity of 5 minus the limit as x approaches negative infinity of 1 over x squared. This we can figure out very quickly and easily. This is just a 5. The other part is what? 0. So the whole thing has a limit of 5. Okay, so now we can actually apply this limit across the board and see what we get. So on the low bound, since we know the limit of this expression is just a 5, this is the negation of that. I mean, you can carry out the process too, distribute. You get negative 5 plus 1 over x squared. It would still give you the negative version of this answer. So we can say that negative 5 is the low bound when we're looking at the limit as x approaches negative infinity of 5x squared minus 1 over x squared plus 10, and 5 is the upper bound. So that circles us all the way back to this one and tells us what? Do I know what the limit is of this? I have a great deal of uncertainty. I've narrowed it down. It's not negative infinity to infinity. It's a better DNE than that. But it's still DNE, right? The limit does not exist because we can't pin down what the actual limit is. So the limit does not exist by the squeeze theorem. And that's what I needed, right? I'm just making sure. Yeah. So, by squeeze theorem. The limit might exist by some other technique, but these questions are asking us to apply the squeeze theorem and basically determine whether or not the squeeze theorem holds. So if you don't get a conclusive answer, you can't just say simply, that the limit does not exist. You know, maybe you go to your calculator and see that the limit is 2.5. That's not the squeeze theorem. The squeeze theorem is not holding up here. The squeeze theorem fails, but that doesn't mean that the limit fails. It doesn't mean that the limit does not exist in general. It does not exist by the squeeze theorem. All right. So further research would be required, I suppose, if you really wanted to pin this down. Okay, so I'll put up the answer key to number 4, or maybe, you know what? I have some free time today. Maybe I'll make a video for that. So sine is between -1 and 1. Cosine cubed also. So add these. Add these. And these also. Definitely has to be between these two numbers in some capacity. So, looking at -2x squared over x squared plus 1, x minus 3. Over same stuff. So I'll apply the limit here. Well, in either case, this distributes. And so if we want to use the behavior model method, you have -2 over x. Then this would correspond to 2 over x, each of which are 0. So we have it. Of that whole shebang, I'll just say f of x